Well, hello folks. This is going to be the second to last problem set examples I'm going to do today. Let me change my pen color to, let's go with blue. So we're talking about chapter 20 problem set B. And what we're going to talk about is what we call in AC currents, how the current can change and how there's a maximum current also as an average current. And we'll talk about this, and when the average current is called root mean squared. So RMS is equal to what we call root mean squared. And now what we do is we got 5 values, and they're going to be positive, negative numbers. So if we take 1, minus 2, 0, 1, and 2, if we average all this, the average will be 0. But that doesn't make any sense because we've got numbers all over the place. The average is really not 0. But what we do is we take the root mean square. That means we square all these. So that's 1, 4, 0, 1, and 4. And then take the average of that, and that's going to be an average of 2. Say 4 plus 1 is 5. Whoops, because we square it. 0 squared is 0. 1 squared is 1. 2 squared is 4. 4, 8, 9, 10. That's 10. We got 5. And then we got 1, 2, 3, 4, 5 numbers. And so the average is going to be 2. And then we take the square root of that. So our actual average is square root of 2. So basically, root mean squared is that the RMS value is equal to, we add everything. This is what this summation is. Add up everything, square things, and add everything out, divide by n, then take the square root. And this is how this works, the RMS value. And what this means is that we have a current maximum, our current RMS, the average current, is slightly less than that because it fluctuates going up and down, up and down, up and down. And so what we need to do, remind ourselves that Imax is always more than IRMS. And we have this factor that we need to realize, 0.707. So 0.707 times that current maximum is the root mean square of the current. And we'll do the same thing for Vmax, and that's going to be the voltage root mean square. And so this 707 is, some of you guys may recognize this in mathematics, and that's going to be 1 over the square root of 2. And that's also important because we need to keep that in our heads. And it's just something that shows up a lot of time in physics and in mathematics, so that 1 over the square root of 2 or the square root of 2 occurs a lot. Now the other equation we're going to see is power. Power is actually equal to current squared times R, and we're going to use this for some of these equations. So here's an example, and this is just something a little bit big. So the world's hydroelectric generation is 1.2 megawatts. We're not going to get it, however. And so the world's RMS current, root mean square current, is this value, 2.2 times 10 to the 10th, and that's our current. And the load overall is this resistance, 6.1 times 10 to the minus 10th. That goes all over the copper lines before it gets to the house. We want to know the maximum AC current and how much power can be supplied. So let's look at RM. So IRMS is equal to, let's see, 2.2 times 10 to the 10th. Now, remember we said IRMS is equal to 0.707 Imax. So we divide both sides by 0.707. And then we have Imax is equal to 2.2 times 10 to the 10th divided by 0.707. And so if we add this to our calculator, 2.2 raised to the 10th divided by 0.707, we should get 3.1 times 10 to the 10th. So that's the Imax of this thing. Now the question is, what is our power? Now power is going to be equal to I squared times R. So the power, that's what we're looking for. It's equal to, let's use the maximum current, 3.1 times 10 to the 10th, and we're going to multiply it by our resistance, and that's going to be the 6.1 times 10 to the minus 10. Now this resistance is basically the resistance through the wire that we have. And with AC currents, even though this is going to be very long, this resistance is fairly constant in the wire, because since the power is going back and forth, the electrons are going back and forth, we don't meet that much resistance, and it's actually very low no matter how many miles of copper wire we have. So 3.1 times, and this is actually, remember, current is squared. 3.1 times 10 to the 10th, we're going to square that, and we're going to multiply by 6.1 raised to the minus 10th, and the power is going to be 5.86 times 10 to the 11th watts, and there's the power for this. And this is the end of the section.